Okay, so next week is reading week, and we are going to finish this week everything to do with particle kinetics. So we will start on your return on rigid body kinematics, which is chapter 5. But to end out this week, we're going to talk about something that is actually one of the more complex parts of the course, and one of the more difficult ones to start with. So we've covered in the first part of chapter 3, first part of chapter 4, sum of forces equals mass times acceleration, and that's Newton's second law. Last week, we were going over work energy, and work energy is kind of nice because you didn't have to worry too much about vectors, and you end up with a nice set of relationships that work for force, velocity, and distance. Finally, you have sum of forces equals m dv dt. And here, these are force, velocity, time questions. So you'll be given something like a 20 Newton force is applied for 0.06 seconds. What is the final velocity of the mass? So it doesn't have to be a curved path, but we can look at a case where we have some sort of motion along a path. And again, you have, say, forces being applied at an angle with respect to the path. At time 1, it's at position 1, time 2, position 2. And in the process of moving there, we can start off and say, well, all of those forces equals mass times acceleration. If we integrate from time 1 to time 2, we end up with equations that look something like this. So you can write that out in that form and recognize right away that this acceleration term can be written as dv dt. So you end up integrating, and it yields force applied over some time is equal to mv2 minus mv1, which is velocity at position 2 minus velocity at position 1. And so these kind of new terms appear. And you can do one other thing. From that, you have sort of a nice set of equations that tell you that if you apply a force for a certain amount of time, you'll have a change in velocity. And that change in velocity can be described here. Now, what you will end up doing with this is turning around and defining something called momentum. Now, unlike the case with work energy where you had a scalar term result, you see here that you still have a vector term. So G depends on direction, and It's just a description of what's happening there. So if I have that, I'm going to have units of mass times length over time with SI units of kilogram meter second, Newton seconds, slug feet seconds, or pound force seconds. All of those will sort of play a role in what you're kind of solving for. But what about this term right here? That term is also kind of interesting, and you can see that it's important to how we're going to solve for problems in the future. And that's just going to be the linear impulse. I haven't decided when I'm going to talk about it, but it's either going to be tomorrow or today, later today, tomorrow, or Friday or Thursday. But angular momentum and angular impulse are also going to be secondary terms you're going to look at too. But you can see that that is just the integral of the area under that curve. And you can describe it by integrating, which is easy. F dt. And it depends on direction. And again, when you're looking at momentum terms, you're going to have vector terms that result and vector terms that start to play a role in terms of the individual distances. So if I write this, or if I take this equation back here, and I just say, okay, I've got f dt equals mv2 minus mv1, I can rewrite that then as the integral of f dt equals g at time t2 minus g at time t1. And I'm always hesitant because different books have different terms for linear momentum, g in this book, L in other books. So you have that you can write, but that's not really the type of equation you want to deal with. It's easy enough that you could say, hey, let's just bring the t1 term to the left-hand side. And we have a g of t1 plus an impulse delivered over time is equal to g at time 2. And that's going to be one of those governing equations you break down into scalar components and solve for in a number of different cases. And all that is initial linear momentum plus an impulse delivered final momentum. And that's going to be our conservation, or I don't want to call it conservation. The impulse momentum principle. So when you're looking at problems in this chapter, or the section of the chapter in this set of assignments, you're looking for problems with force, velocity, and time, and you're using the impulse momentum properties to solve for it. And I ended up not giving myself enough room. So So the particle change of momentum is equal to, over delta t is equal to, I could probably make that nicer, over some interval is equal to the impulse imparted to the particle over that time. And of course I can write that as force over time is equal to g dot. So dg dt. So from that I have a couple other things that I can do. I can recognize that if this is the force, this is the time, I will have an average force imparted over that time that is the equivalent to that area under the curve. So and so you often are interested not necessarily in knowing every possible variation on the force over time. You just want to know what the average is over the interval of interest. So from t1 to t2, you calculate the impulse delivered. That's your difference in momentum. You divide by the time it took. Ugh. I'm going to have to stretch that out a little bit when I reorganize things. So what happens if you have a set of particles, a system of particles that you're looking at? So for example here, I have a number of particles, 1, 2, and 3, that I'm looking at. Into each of these forces, or into each of these particles, there's an internal force, F32, F31, corresponding F13, F12, F21 to F12, F23 back to F32. In there also, I have a number of external forces, and those are listed in purple. And so F1, 2, and 3. And the distances with respect to an XYZ coordinate system is I, J, and K. And the distance R3, R1, R2 to each of those. I haven't talked about G yet, but I'll talk about that in just now, or soon. So if I want to know what the external, or define the external force, I'll define it for each particle as F sub I is the external force on particle I. Then I have F sub ij, which is the internal force on particle I due to particle j. So in this case I've got 3, so I end up with 6 internal forces I have to deal with. And if I look at what's happening to the individual particle I, I can write it as particle I is going to be the sum of the external or internal forces plus the external forces acting on it. And it looks like this. So all of the external forces acting on particle I, all of the internal forces acting on particle I from, say, for example, if I'm looking at particle 1, F31 and F21, and that equals to time rate of change of momentum of particle I. So if I look at the total force, external force, and total momentum, I'm going to have sum of forces is equal to I equals 1 to the number of particles, F sub I, and G equals, again, same thing, I equals 1 to N G sub I. The only thing left are the internal forces. And the internal forces are just going to be the sum of I equals 1 to N, J equals 1 to N, Fij, where I does not equal J. And that should equal 0. So here, I'm not worried about distances. I'm not worried about travel because there's no internal component that's going to appear, and that will sort of disappear from my expression. I'm going to regret this. If I sum over the entire system then, F is equal to G, and yeah, it looks a lot like Newton's second law, but it's also sort of dealing with a slight difference in definition, and it's called Euler's first law. As far as you're concerned, you can treat it as Newton's second law, and that's okay. But just for completeness, I'm going to mention that. G is equal to all of those individual moments or momenta, and it will equal mvg. Now, if you look over here, that's G, which is the center of mass. And F is equal to d dt of mvg, which is equal to mag. And so you have the same sort of thing, but the only problem you have at this point is how do you get G? So in this particular case, x sub g is equal to the sum of mi xi over the sum of all particles. So you take the average, the weighted average of all of the particles and where they are relative to your origin. Oh, that's better on this. Here, with respect to x, maybe a different color, x, x, and x. You add them up, multiply by their individual masses, and then divide by the total mass of the system. So if you have a bowling ball and a couple feathers, everything will be biased towards the bowling ball. If everything is equally spread out, it will be an equal spread in a linear sort of combination. Now, that's the x location. No surprises here. Y of g and zg are going to be the same thing. So you add up all of the terms, you add up all of the locations, and you end up with a term that sort of describes the average location of all of the system of particles. And that may change with time as things sort of separate and the particles spread out and things happen. And there are a lot of really exciting computer programs now and computer models based on looking at particle displacements. But one of the primary and fundamental things that you do as you look at these models is exactly that. Where is the center of mass of your object? Yeah, maybe I'll do that. So another thing that happens in a lot of dynamics classes, everybody plays pool. And so you have here two particles, two balls, the red 3 and the black 8, and you're going to have a couple things happening, but you got an impact that has occurred. And so you have conservation of linear momentum. You have two balls that hit each other. And if you look at the free body diagram for the forces acting on ball 8, it's this right here. There's no weight that appears in this problem because it's occurring on a pool table. And because it's occurring on a pool table, weight is acting down through the screen. So you have two particles. So I can define a coordinate system that aligns with the impact. And so I've defined here unit vectors B and A, and B is the tangent to the impact, and A is along the line of the impact. The only force that's being applied is acting along A, and that's force 8. So when they come into contact, it sort of looks like that. There's no external force. So I can write G1 equals G2. And so my conserved terms in this case are just going to be mass V of ball 3 at time 1 plus mass of V of ball 8 at time 1 equals mass of ball V at time 2, V3, I'm not going to call it just mass, V3 at time 2. You'll notice these are vectors, if I can draw them. Mass V8 time 2. So between time 1 and time 2, I have a conserved momenta. And so the initial momentum of the system at time 1 is the final momentum of the system at time 2. So this is always the case when you have an isolated system for which there is no interaction with the surroundings. Yeah. So now you have three different approaches to take with problems with force and acceleration, Newtonian mechanics, second law, force, displacement, and velocity, work, energy, and today, forces, time, and velocity, which are linear impulse and momenta. Again, the next step is to have rotational systems, where you introduce some sort of moment, and you calculate times and velocity, and that's coming up, but it's angular impulse and momenta, which will be there. Any questions on this? These are hard to visualize. Again, as much as possible, as you're dealing with problems with this, always make sure to do something where you're looking at, not there, where you're looking at these problems from the point of view of drawing out what's happening, making sure you know what your conservation equations are and when they hold true. So I have a baseball, and I have placed it on a tee. And in the process of placing it on the tee, I'm going to hit it. And the ball leaves the tee. So the mass of the baseball, 40 grams. The ball leaves the tee at 35 meters per second at 40 degrees to the horizontal. What is the impulse delivered when the force has been applied for 0.03 seconds? Okay. So often it's very helpful to draw out that momentum type diagram or momentum diagram where you put the ball at the 3 equation points. So starting out, you have mv1, which is equal to 0. You have a force at 40 degrees that's been applied to the horizontal. So 40 degrees to the horizontal, force F is applied, and it's applied for 0.03 seconds. So that's a plus, and that's going to equal the final velocity of the system. And you're given, it leaves the t at 35 meters per second. Again, 40 degrees. I should. But I kind of know what direction it's going to be applied, that force, because it has to be applied in the same direction as the motion occurred. There's nothing in this diagram to counteract the final velocity. So if that's the only external force, it has to be applied at 40 degrees. So I can write this as zero plus the integral from 0 to 0.003 seconds f dt, which equals to mv2 of the system. 0 because it starts from rest. The force is applied for 0.003 seconds. And I was asked for an impulse. So I can say force average 0 to 0.003 dt is equal to 0.04 kilograms at 35 meters per second. Now what I've done here is I've already... Do
you not consider gravity over the 0.003 seconds?
I'm going to talk about that in a second. It's a good question. So one of the questions that is going to happen a lot is what happened to the weight here? And how does the weight play a role in this? So if you look at it, you sort of say, okay, F average integrated 0.003. Oh no, I've already done that. Ooh. Force average is equal to 467 newtons at an angle of 40 degrees with respect to the horizontal. Now, one question that was just raised, and it's a typical question to ask, is what about the impact of the weight? Because the weight is also applied. You can sort of treat it for the time that this hit has occurred. And in that case, you could sort of say, well, mg delta t over that same time is going to be 0.04 kilograms, 9.81 meters per second squared, and 0.03 seconds. And if you do that, you'll find that the contribution of the weight, 1 Newton seconds, is 0.0018 or 118 Newton seconds. And so if you kind of add that into the impulse that's delivered over that time, it's a relatively small component and it doesn't change your significant figures. There are going to be cases, if we, for example, if we ask on an exam, we'll sort of give you a hint to the effect that include the effect of weight, but typically weight is not going to be important. Go ahead.
Could we not say that in that moment the ball is still like supported on the T and then that has a normal force counteracting?
At the very beginning of the problem, but remember, I'm not looking at the very beginning of the problem. I'm acting, the problem has started Now an impulse is delivered right away, and I don't know what's going to happen here. So it's going to be leaving at the same time. So it's a very short period of time over which it occurs. The normal's not playing much of a role either.
So the normal's not active.
Normal's not doing very much. Okay, not worth worrying about. Oh, I did have an absolute dependent motion. That was the one I wanted to do. Okay. Now I regret it because I just erased this figure. All right. So I have an absolute dependent motion problem. Here I have a mass which is attached to a pulley. The pulley is attached to the upper ceiling. It goes around. There's a pulley here. It goes around. It comes back down, and it attaches to the mass over here. And this is a motor. And I'm going to just label these as A and B. And I have motor So for the first 1.4 seconds, ooh. So for the first 1.4 seconds, the motor is providing a time-varying force of 1 plus t over tau. Tau is equal to 0.5 seconds. F naught is equal to 175 newtons. What else do I have? T1 equals 0. T2, that's not a very nice T. T1, T2 equals 1.4 seconds. So the first thing I'm going to do in all of this is the same thing I would do in any problem that I faced in this course, which is to draw out the free body diagram. And I'm going to cheat a little bit and sort of recognize that I can combine all of the cables on the top. So instead of drawing in a diagram with this, and then this, and then this, I'm going to just combine that part of the diagram into one and just say, okay, look, I've got 3FC going up, and I have weight acting downward. Now, I'm not expecting to have any type of side-to-side motion, and typically in a problem like this, I wouldn't have any side-to-side motion. I am including weight here because this is a much longer time and it's a much lower force. So if I do that, I can write my expression in this form right here. So the nice thing in this particular case is the weight is going to go outside. That's constant, but the F sub c is a little bit of a pain in the neck. And the F sub c is equal to F naught 1 plus t over tau. Vy1 is equal to 0, and if I solve through for this problem, and recognize that my T1 is equal to 0, I end up with this form right here. So just substituting directly into the integral for f sub c, solving the integral, I end up with 3 times f naught t2 plus t2 squared over 2 tau. The t1 terms all go away because that's 0. On the next term, I just have weight times time, t2, and that total value is the impulse delivered to determine the final velocity of the block. So lining everything up, I end up with this expression right here, which is just the final velocity in terms of t2 and 18.37 meters per second. You can see it's a pretty impressive sort of acceleration if you figure out 18 divided by 1, 18 meters per second squared. That's pretty good. Any questions on this? Go ahead. You were given that at the very beginning of the problem. Yeah. So tau is just a time constant, and tau is equal to 0.5 seconds. So in this case, at time equals 0, the force of the motor is just going to be F naught. At time equals 0.5 seconds, it'll be 1 plus 1 and 2 F naught. At 1.5 seconds, it'll be 3 plus 1. So you're adding, it's an additive term, and it tells you you have a time-varying force. And it makes for an interesting integral. So there you go. So as you're looking at these problems, the number one thing, again, draw the free body diagram. Once you draw the free body diagram, you can say, hey, that force is going to be like this. This is how it works. You need to do this with absolute dependent motion and solve for different types of problems. Any other questions on this? Just see if I can find this. Otherwise, I'll go to that. Okay, so similar types of problems are going to occur. You're going to be dealing with problems in this course where you have forces that vary with time, and as you calculate what's happening, you have to determine what's going on. So here, I have a motor, I have a log, and I have a rope. So the rope is attached to the log, and I'm trying to drag the log from the left to the right. So I have a mass of the log of 500 kilograms. I'm given mu sub s of 0.5 and mu sub k equal to 0.4. So now I know pretty quickly that this problem will require me to sort of solve through for the free body diagram to determine when slip is going to occur. You're also given a diagram for the tension in the cable. Or in the rope. So the tension as a function of newtons is going to look something like this. It will reach a maximum value of 6,400 newtons at 4 seconds. And then after that, it will have a constant tension in the cable. You're given a function of 400 t squared for that tension as it rises from 0 to its maximum value. So if I take my log and I put all of the forces acting on it, I have the weight acting downwards, I have the normal force acting upwards. I have tension in the cable, and I have mu sub s n, which is the point where I'm going to look for impending slip. So if I do sum of forces in x, I will get t minus mu sub s n is equal to 0, and t in this case will be mu sub s n, which yields, if you put numbers in and solve for the weight and all the rest, 2452.5 newtons. That's going to occur at time equal to 2.48 seconds. So 2.5 seconds in. So now I know that I will be pulling on the log for 2.5 seconds before I'll see any motion. And afterwards, I will not be at my maximum value of force for another 1.5 seconds, 1.52 seconds. So if I stop with this,